Hi everyone, welcome back to Mathematics 0110. This lesson is about something called related rates, and it's our introduction to word problems in calculus. I want to take you through some simpler examples before we get to more challenging examples. Part of what we do inside this section is we build mathematical models. Some of these models are based on geometry. Some of these models are based on understanding that comes from business or understanding that comes from everyday common sense. So let's look at this first example where we have John using some amount of electricity, H units, whatever the units are, and he pays P dollars per unit. Part A is asking us for the mathematical expression that describes John's total monthly electricity cost. So let's just, before we write down a formula, let's think about this logically. If John uses 1 unit of electricity per month, and let's say that unit costs $5, then his total monthly cost is going to be 1 times 5, so $5. Let's say he uses 2 units, and each unit costs $5, and his total electricity cost is going to be 2 times 5, which is $10. So a mathematical statement that would seem reasonable to describe his total cost is total cost is equal to the number of units, H, times the number of dollars per unit, and multiply them together. Like if you want to buy 100 of something and each of them costs $3 and your total cost is going to be $300. It's just that. It's just that mathematical expression. The number of things you buy multiplied by the cost of each of those things. Okay, part B. If H and P are functions of time, what expression yields the rate of change of John's total monthly electricity cost? So I'm going to go back to part A. I'm going to give this a different name. I'm going to call it T. Total cost is H times P. Rate of change means derivative. And I really should say instantaneous rate of change. If this was a test question, we would attach that word instantaneous to distinguish the derivative from the average rate of change. So this should say instantaneous rate of change. So that means we want T prime, we want the derivative of T. Now, we have 2 functions multiplied together. H is a function T of time and P is a function of time. So we need a product rule to take that derivative. We have the first function times the derivative of the second plus the second function times the derivative of the first. And I'm going to put product rule here. It's the same product rule with H and P as we have with A and B, just different letters. Okay, next part. At this time, John uses 50 units of electricity. So H equals 50. I'm going to convert the paragraph into math as we read the paragraph, and pays $2 per unit. So P is equal to 2. What is the instantaneous rate of change of John's electricity cost? So we want T prime if his energy usage is increasing by 10 units per month. So we have to be careful interpreting statements like this. Energy usage increases by 10 units per month. So the number of units of electricity per month is 50. The rate of increase is 10. So what it's talking about is a rate of change, a derivative. So I'm going to say H prime is equal to 10. And his energy cost per unit remains the same. So if the energy cost per unit remains the same, that means it's not changing, which means its rate of change is 0. So P prime equals 0. So we can put all that data together and use our result from part B that tells us that T prime is equal to H P prime plus PH prime, and plug in the data. So H was 50, P prime is 0, plus P is 2, and H prime is 10. And then simplify. 50 times 0 is 0, 2 times 10 is 20. So what this is saying is that the average rate of change of monthly cost is $20. It's going to cost him $20 more, which makes sense. Think about what's happening. He's using 10 more units that month, and the cost per unit is $2. So 10 times 2, his cost should go up by $20. The result isn't surprising. It should be completely consistent with our everyday experience. Let's look at the next example that has a non-zero change to the price. So at this time, John uses 50 units of energy per month and pays $2 per unit. So that part's the same. H is 50. P is equal to 2. What is the instant change rate of change John's electricity cost? So that's T prime. We want T prime again. That's our goal. If his energy usage does not change, so that means H prime is equal to 0. Put that down on the bottom left. If his usage is not changing, then the rate of change of the usage is 0, and then his energy cost increases by $1 per unit. So that's P prime rather. So P prime is equal to 1. So he's not using any extra energy, but the price is increasing by $1 per unit. We can put all this together, go back to our result from part B, which gave us our rate of change of the total price, HP prime plus PH prime, and then sub in our data. So 50 times 1 plus 2 times 0, which simplifies to 50 plus 0, which is 50. And that makes sense. Every single unit went up in price by $1. He had 50 of those units, so the total increase will be $50. Okay, and then last example, I'll write down the data as we read. John uses 50 units of energy, so H is 50, and pays $2 per unit, so P is 2. What is the interchange rate of change of John's? So we want T prime. It's important to write down what the goal is, so you're solving for the right thing. Sometimes it's asking for P prime, so it's the rate of change of one of the prices that goes in as an ingredient, which will require us to rearrange. But this one's straightforward, it's just asking for something that's already isolated. And then his energy usage decreases. Aha, there's a special word here. It is a very important word in this unit. And actually for the rest of the course, his energy usage decreases by 25 units per month. So H prime is equal to negative 25. So our negative rate of change is a decrease in quantity, a positive rate of change is an increase in quantity. We know that already from thinking about the pictures of bank accounts going up and down, and calculating average rates of change, and understanding the association between the instantaneous rate of change and the average rate of change. So the idea that a negative derivative means decreasing is already kind of part of our vocabulary of calculus. And then the last thing is per unit energy cost increases by $1 per month. So even though he's using less energy, the price per unit is going up. P prime is equal to positive 1, positive because it's an increase in that rate, an increase in that quantity. Okay, so our formula again, T prime is equal to H P prime plus PH prime. We can sub in our data. So H is 50, P prime is 1, plus P is 2, and then h prime is negative 25. So we simplify, we get 50 minus 50, we get 0. So the net effect of a $1 increase per unit for the bill and a 25, so that was a $1 increase per unit, and then a decrease of 25 units of energy, the net result is there's no change in the total price that John's going to pay. And you think about this logically, what's happening is he's cutting his energy usage in half. He's subtracting 25 from 50, resulting in 50. And then his price, his electricity price, is doubling. Not doubling, it's going up, let's see. Yeah, it's going up 50%. So it's going up from $2 to $3. So both of those changes balance each other out, resulting in a net change to his bill of $0. Well, you may have been able to reason through these calculations without using a product rule, without using calculus, but maybe not. It gives us a systematic way to think about rates of change of quantities that have several moving parts, that have several things that we're allowed to vary at the same time. So a common place where we have a type of function that has multiple inputs might be in a financial model. So when I'm going to show you our toy models, realistic models don't look like this. Realistic models are based on this type of statistical analysis. But this gives you an idea of how really simple models can be built. So we want a model of a stock price as a function of time. It would never be in years, but for the sake of argument, let's just say years. Into this model, we might have the interest rate. We might have, let's say, some other inputs like the price of some other stocks, or maybe just one stock, and perhaps the price of US Treasury bonds. There might be 100 or 200 or 300 inputs that go into this model, but in this simple example, we only have 3 inputs: interest rate, another stock price, and treasury bond prices. Suppose after doing some analysis, we construct a simple linear model that connects the price of this stock to the prices of those 3 other things. And it's found that the price of the stock is equal to 30 times the interest rate plus 3 times the price of that other stock, maybe it's Microsoft because it starts with an M, minus 10 times the bond price. Then we can talk about the rate of change of the price of the stock according to this model is going to be given by the derivative of the ingredients of the model. So 30 times R prime plus 3 times M prime minus 10 times B prime. Since those components of the model are separated from each other by plus signs or minus signs, we can use the rules of calculus to apply the derivative to each piece separately. And we can also factor the constants in front of the derivative. So the 30 comes out, so it's the derivative of 30 times R is 30 times R prime, and then we do the same for the other pieces. Maybe we have some other data. Maybe we expect the interest rate to, let's see, it says R prime of t is equal to 1 unit per year, so let's say we're expecting it to go up on average by 1 unit this year. We're expecting another stock price to go down $2 per year, and then we're expecting the US Treasury bond prices to increase $2 this year. If our model is accurate, we'll be able to take those other predictions, those predictions for R prime, M prime, and B prime, and feed them into our expression for P prime. So let's do that. Our P prime of t is 30 times R prime, so 30 times 1, plus 3 times N prime, so 3 times negative 2, since it was decreasing, was negative $2 per year, so negative 2, minus 10 times B prime, so 10 times positive 2, and then so that's 30 minus 6 minus 20, which works out to 4. So the prediction that this type of model would make is that the stock price will go up by $4 in 1 year. Again, this is not very realistic. This is not how it actually works, but it gives you an idea about how you can relate a change in one quantity to a change in another quantity, and maybe a change in several quantities into a change in one quantity. look at another kind of silly example before we get into the more realistic examples. We have here a knob maker with daily revenue of $500. And the revenue is increasing at a rate of $5 per day. So I'm going to mathematize that. I'm going to say revenue is equal to 500 and R prime is equal to 5. Daily costs, so I'll use a different letter for that. Daily costs are currently 400, and they're decreasing at a rate of $2 per day. So C prime is equal to -2. I'm going to highlight where the source of the negative is from the word decreasing. A negative rate of change is a negative derivative, or decreasing rate of change is a negative derivative, sorry. Now, for the next part. Here's the question, what is the rate of change of daily profit at this time? Hint, profit is equal to revenue minus cost. So we have to create a function. This is not a business class or a management class, so I put the formula here. Profit is equal to revenue minus cost. We're looking for a rate of change of profit. So P is equal to R minus C, and we want the rate of change of P. We want P prime. How do we find P prime? Well, we take the derivative. P prime is equal to the derivative of R is R prime. Derivative of C is C prime. Now, before we start plugging numbers in, let's think logically about what's happening. Our revenue is going up $5 per day. Our costs are going down $2 per day. How much better off tomorrow are we going to be compared to today? So tomorrow we make $5 more, and it costs us to run our business $2 less. So we're going to be better off by $7. $2 on the cost side is decreasing, $5 on the revenue side increasing. So overall, our position that day, tomorrow, is going to be $7 better. And the next day is $7 better than that. And it'll keep getting better and better and better at a rate of $7 per day. Let's plug in the math. So the math says we have 5, subtract -2. So 5 plus 2 equals 7. So the math matches up with our intuition once again. We didn't really need calculus to answer this question, but in the following questions we're going to work on, we won't be able to rely on our intuition in this way. We'll have to rely on this type of formalism, this type of a setup of statements that will allow us to come to a reasonable conclusion, not necessarily relying on our intuition. And we'll do that in the next video.